Welcome. When I define partial derivatives, I mentioned how we can interpret them as a rate of change. Just as we did in chapter 11, we can use this to talk about rates of change of one quantity with respect to another. In economics, these are often referred to as marginal such and such. So if you have a joint cost function for two products, then the partial derivative with respect to the quantity produced of each product is called the marginal cost with respect to that product. If you're producing two products A and B, the joint cost function is C, then dC over dQA, where QA is the quantity produced of product A, is called the marginal cost with respect to A, and dC over dQ is called the marginal cost with respect to B. Kind of problems you will find in homework consist of just things where they give you the function and ask for the marginal this or that. So it just means you have to take the partial derivative. Like in our next two examples. In the first one, we are given the joint cost function. They're asking us to find the marginal cost with respect to the first product at a certain production level and explain in words what it means. First, we'll just do the mathematical calculation. And to do this, I'm going to write this expression using fractional exponents, which is what I've done here. To find the partial derivative, since I have a product here, I have to use the product rule. Because the last term is an absolute constant. It doesn't change at all, so its derivative is 0. So I really need to just do this derivative. I'm differentiating with respect to QA, so I treat QB as if it's a constant. First factor is QA. The derivative of QA with respect to QA is 1 times second factor, QA plus QB to the power 1/2, plus the first factor QA times derivative of the second factor, QA plus QB to the power 1/2. Since I have power of an expression, I have to use the chain rule in combination with the power rule. First, I differentiate for the exponent which is outside. So I get 1/2 times the expression inside the parenthesis to the power 1/2 minus 1. And 1/2 minus 1 is negative 1/2 times the derivative of the inside. The inside is QA plus QB. Its derivative is 1 plus 0. Since I'm differentiating with respect to QA, I treat QB as if it's a constant. To find the marginal cost when QA is 40 and QB is 60, I just plug those numbers in for QA and QB respectively and calculate, which comes out to be 12. So what does it mean? It means that if you hold the production level of product B fixed, so you keep producing only 60 units of B per time period, but increase the production of product A, then cost will increase at the rate 12 monetary units per unit of A. So if you increase the production of A by 1 unit, but keep the production level for B at 60 units, the cost will go up by about 12. Another situation where you have functions of two variables is what's called productivity function. Productivity function describes the production given certain levels of various inputs. One of the simplest cases is where we look only at labor and capital and ignore other things. This is the simpler kind of factories that they used to have in 19th century. So this is the origin of this type of problem. So here I'm given some productivity function and I have to find the marginal productivity with respect to labor. By convention, we use L for labor, K for capital. Of course, we don't want to use C because we use C for cost. So marginal productivity with respect to labor means you keep the capital input constant and increase only labor. So you treat K as a constant, differentiate with respect to L. And since I have just a polynomial, that's easy. I differentiate term by term. In the first term, I have 15Lk. So it's 15K times L. I treat K as if it's a constant since I'm differentiating with respect to L. So I get 15K times 1 or 15K. In the second term, I have minus 3L squared. The derivative with respect to L is minus 6L. In the third term, I have only K. Its derivative is 0 since I'm holding K constant. The last term is an absolute constant. It doesn't change at all, so its derivative is 0. So I get 15K from the first term, minus 6L from the second, 0 from third and fourth term.